Okay, so this is joint work with there's Yang Tsai and Nikhil Devanur and Preston McAfee, who I don't think is in this room. Okay, yeah. And so I'm going to talk about proportional complementarities and simplicity as joint work then. Okay, so the running example is going to be pricing Microsoft Office products because, Nikhil is at Microsoft, Preston used to be at Microsoft, I was an intern at Microsoft during this project. Okay, so we're talking about Microsoft. And so how should we price them? Should we price them separately in specific bundles, all together, some combination? We're going to talk about Office products and how to price them. Okay? And when we're talking about pricing items, we should know that optimal pricings are hard, even in the simplest of cases. Okay? But recently what we know is that simple pricings are near optimal, right? And so our favorite mechanisms, we should either sell them separately, each item separately at a price, or all together in one grand bundle. And the better of these two mechanisms, or slight variance thereof, give a constant factor approximation for all of these settings, right? And so this was originally proposed in the Fox 2014 paper by Babayev et al. And since then has been modified, well, it actually started in 2010 with the unit demand paper, but has been modified for all of these settings. Okay, so we know that the better of these two mechanisms are great, but as you will notice, all of these settings are complement-free, and as I said, we want to talk about complementarities. Okay, and also what you'll notice is that selling everything together in one grand bundle makes the most sense when we have complements, right? If we have complements between the item, if you derive some extra value from buying two items together, then it makes more sense to sell them in a bundle because you can extract more revenue this way, okay? So here's one model for complements. The positive hypergraph model was proposed by Abraham et al. And it's as follows. Suppose you have PowerPoint and Excel and Word, okay? And the buyer has a value for each of these. But you shouldn't think of them as the value for the items. You should think of them as the value for the activities of using just PowerPoint and just Excel and just Word. And then the buyer is also going to have a value for using PowerPoint and Excel together. That's the activity of using PowerPoint and Excel together. And the buyer separately has the value for using PowerPoint and separately has the value for using Excel, and so on for every pair, and also for the combination of all three. And then the buyer's value for the set of any items is the combination of the activities they can do with the single item and the pair of items and so on, okay? And so a parameter of this is k, which is the size of the largest hyperedge. So in this example, that would be 3 because we have the hyperedge including all three items. And this was extended to the MPHK model by Fega et al. Because then you can take the maximum over multiple positive hypergraphs, all of size k, again with this parameter. Okay, so this is one restricted model for complements that has been used for welfare maximization. Okay, so then there's this paper that does pricing with this positive hypergraph, actually the maximum positive hypergraph model, okay, by Eden et al. In 2017 in EC. And so what they show is that for the actually MPH model, the better of selling separately in the grand bundle, these mechanisms that we've been talking about, give an order D approximation. What's D? I was just talking about K. I switched letters. Okay, so what D is the maximum degree D. Okay, so this is the maximum number of edges that any item appears in. Okay, as opposed to K, which was the size of the largest hyperedge. Note that the approximation is actually exponential in K. So now we've changed factors, and all of the previous models that use this actually had welfare approximations in K. Further, note that for some examples, for example, the complete hypergraph, I should say hypergraph, that has k equals log n, so this is the hypergraph where every edge is of size log n, has d being n choose log n. So k can be very different than d in this case, and the approximations look very different, so maybe we would want an approximation that's more like k, like the welfare approximations. And further, this paper needs the assumption that every activity valuation is drawn independently. So what does this mean? This means that the valuation for Excel and Word used together is drawn independently from the value for Excel is drawn independently from the value for Word. So if your value for Excel is high and your value for Word is high, it has no bearing on how your value for Excel and Word is drawn. Okay? Okay, so we found this assumption unrealistic, but without it, you have this negative approximation gap that we know. And so we decided to come up with a new model. Okay, and so here's how our model looks. We have PowerPoint and Excel, and the buyer has some value for each of them. And we're going to think of these as the base valuations for the items. Okay? So perhaps $20 and $10. And then the buyer gets some boost from having Excel in addition to having PowerPoint. So you should think of this as the boost from making a chart in Excel and then dragging it into PowerPoint. Okay? And this is a market parameter. It's fixed because the way you use these products together are approximately fixed for everyone. Okay? And so this is ADA Excel to PowerPoint, the boost you get from having Excel when you already own PowerPoint, and it might be 0.25 for this market. Okay? And then your valuation is this additional boost times your base valuation. Okay, so in this case, you get an extra $5 if you own Excel in addition to owning PowerPoint. This is just your value for PowerPoint. I'm not talking about your value for Excel. I'm talking about your value for PowerPoint when you also get Excel. Okay? However, if your value for PowerPoint were $30, then you get the same boost factor, but now it's time your base valuation, and so your boost would be $7.50. Okay? You could have asymmetric boosts. So maybe having PowerPoint doesn't help you out as much with having Excel, so it's only 0.1. And then your value for the set is your base valuation for having PowerPoint, 1 times your value for PowerPoint, plus the boost you get from having Excel. And then your value for Excel plus the boost you get from having PowerPoint. Okay, and in this case, it happens to be $36. Okay, is that clear? Okay. And of course, you could add on Word and have boost for Word. And then your value for the set is 1 plus the boost from PowerPoint plus the boost from Word times your value for PowerPoint, and so on. Okay? And further, we can make it hypergraphic as well. You can have a hyperedge that says if you get PowerPoint and Excel, there's something you can do with the two of them that then boosts your value for Word. Okay? So this is our model. Okay. And again, these parameters are fixed for the buyer. And they're given to you in this graph, these ADAs. So what does the seller know? They know the independent item distributions for these base valuations for each item. And they know these market parameters, the ADAs. But they do not know the realizations of the values. So where does this model come from? The motivation comes from what I don't believe exists anymore, but at the time was the Microsoft pricing engine. And the idea was that we realistically know these market parameters because we have so much data. So Microsoft was running this product that said, let's take a company, we're trying to help you price your items, we'll take in all your data for you, we'll observe, like, how should you price your orange juice, okay? We'll say, like, what are the promotions you've been running? Should you bundle any products together? Are there any complementarities between them? How should you price your items? Okay? But the problem was, prior work doesn't really tell us how should we use simple pricing schemes when we have complementarities with these proportional boosts, okay? And the mechanism that we want to use is this new mechanism that we propose called the separate free mechanism. So what does this do? It posts every item at a price, but the price for all the items on the left-hand side, which is going to be the free set, are 0, okay? So all the items are free, and you can just take them. So the buyer's definitely going to take all the items on the left. And all the items on the right are going to have some non-zero price set on them, okay? And what price are they going to be? Well, if we know that the buyer is going to take all the free items, then the buyer is definitely going to get all the boosts from all the items that are free, right? So we can then take PowerPoint, for example, and inflate the price of PowerPoint by the boost of all of the items that are being given away for free, and inflate this price by the boost of everything that's free, okay? And what we'll use is the Myerson reserve price, but I'll get into that. Okay, so that's our mechanism, and now I'll get into why we can use this mechanism. So what our result is that the better of this separate free mechanism, not just selling separately, but the separate free mechanism and grand bundling gives a 12 approximation to the optimal revenue in this proportional complement setting and expectation when we're just dealing with pairwise complements. And I will deal with the whole maximum over hypergraphic complements, but I'll just start with pairwise complements to do something simple for a brief, okay? So this is, again, our separate free mechanism on the left and selling the grand bundle on the right. Okay, so the first thing we need to do if we're going to approximate revenue is get an upper bound on the optimal revenue. So suppose this is the ADAs that we're given in a graph. Okay. Yes?
For the separate free mechanism, you also need to decide about the partition.
Exactly, yeah. Okay, spoiler alert, it's going to be random. Yeah.
Is it going to be random?
That's cheating. But I'm not telling you how it's going to be random. It's going to be uniformly for this one. Okay, spoilers. Okay, but it's more complex for the hypergraphs. Okay, so we need an upper bound. We're given our graph. This is our proportional complement setting, and this is going to be our etas. I know I drew a complete graph here, but it doesn't have to be a complete graph, so I'm sorry if this is misleading. Hopefully it's no longer misleading. Okay, and we've got some distribution. So for example, we have some distribution that says our probability that the buyer's value for item 4 is greater than X is whatever, okay? What I want to do is I want to upper bound it with a different setting where I'm just going to assume that I'm getting all the boosts, okay? Even if I'm not, this is like hugely inflated. Let's just pretend that I'm getting all the boosts as if I'm getting all the other items. We're getting all the complementarities, okay? And so this distribution is just going to have the exact same probability distribution as if I'm getting this new V hat 4 is the same as the full boost of 4 times X, okay? So it's hugely inflated, okay? And then I'm going to take these new hugely inflated value distributions and just pretend they're additive, okay? So I'm gonna call this fully boosted additive. So I went from this proportional complement setting and I'm upper bounding it by this fully boosted additive setting, okay? And it turns out that the revenue in this fully boosted additive setting is much more. This is not obvious. It should be obvious that the value in the fully boosted additive setting is way more, but the revenue being much more is actually not obvious due to revenue non-monotonicity. The way we prove this is actually going through duality, using duality similar to Ming Fei's talk, but I'm not going to show you it through this short talk. But we use this like nice dual covering from this fully boosted setting to the proportional complement setting, okay? Okay, so this is our upper bound, this hugely inflated, fully boosted setting that is now additive. So we just take our fully boosted items that are way higher distributions, and we just add up the items we get. No more complements, okay? Cool, so we're gonna upper bound the optimal revenue in the proportional complement setting by the optimal revenue in the fully boosted additive setting. Well, now we have an additive setting, and we have results for additive settings with simple mechanisms. So we know that we can just bound it by the separate revenue and the grand bundle revenue using a result from Babayev et al. These are maybe slightly different numbers than you're expecting because we tweak their proof very slightly in an appendix of our paper, and if it doesn't look different to you, don't worry about it. Okay. So bounding the grand bundle in the fully boosted additive setting is very easy because in the fully boosted setting, we're pretending they're getting all of the boosts, and when you get the grand bundle in the complement setting, you get all of the boosts. So selling the grand bundle is the same in these two settings. So the revenue from selling the grand bundle in these two settings is the same, okay? So all that's left is to bound is our fully boosted additive separate setting. So how can we approximate this? This is quite inflated, and we need to figure out how to approximate this. Okay, that's what's left. So let's talk about what this separate revenue in the fully boosted additive setting is, okay? Let's start from the basics. What's separate revenue, okay? We set a reserve price for some item I. We just maximize the price for the distribution, right? That's R. What's the revenue from the reserve price? Let's call it capital RI for that item I. Okay, so now we have a bunch of items. We set R on each one. And then our separate revenue, when we have a bunch of items and we post the reserve price on each item, is just summing up the capital R's. Cool. Now we go to the fully boosted setting. And what happens? We set our reserve price is going to be the full boost times R, because again, our probability distribution is just the same, but everything is increased by that full boost. Okay, so then what's our revenue from a single item? What's our revenue from item 6 if this is our reserve price for item 6 in the fully boosted setting? It's just the full boost times capital R6, okay? Which means that our fully boosted separate revenue is just full boost times R for each item, summed up, okay? So that's what we're trying to bound, this fully boosted separate revenue. And we want to bound it with some constant times the revenue from separate free in the proportional complement setting. Okay, so how are we going to do that? I'm going to construct a graph for you, okay? So suppose we have somehow distributed the items into the free set and the price set, and we set a price on each item that is just the boost from the free set times their Meyerson reserve. Okay, what's a lower bound on this? Suppose I only have one item in the price set. Then what's the revenue I'm getting? It's just going to be the boost from the free set times the Meyerson revenue, okay? And a lower bound is just summing that up because you're only going to get a higher chance of buying if you count the complementarities between the priced items. The buyer has complementarities, but it only increases the chances that they're going to buy these items, okay? If they like items 2 and 4 together, it's just going to make them more likely to buy items 2 and 4 together. Okay, let's break this down. This is just the boosts from the free set plus the 1 for the base valuation is what the F boost I really means. Okay, and so what does my graph construction look like? Well, going into 2, that means that I have the eta from 1 times r. I just need to add that times r. And I'm going to do that for every edge. I'm just going to take my same graph as before, but now going into every, my eta 32 is now eta 32 times r3, because I need to multiply by r times what it's going into to account for the fact that we're going to multiply by ri for what it's boosting. But we're missing the 1 here for the base valuation. So I'm going to add a source node, and on that edge, I'm going to add an r for the base valuation, and do that for all the nodes. And now what you'll notice is that a cut from the source node plus the free set to the price set has exactly this weight. Okay? So a cut from the source node plus the free set to the price set has exactly the weight that's a lower bound on our separate free mechanism. Okay? So our goal was to bound the fully boosted separate revenue. But what we notice is that this, if we look at what the full boost actually is, it's just the sum of all the etas plus 1, which is exactly the sum of all the edge weights. And again, a lower bound on the separate free mechanism was just a cut from the source node plus the free set to the price set. So what does that mean is that we can just take every item to be free independently with probability 1/2, and we get a random cut, which captures each edge with probability 1/4 because it's directional random cut. And so that means that our fully boosted separate revenue is bounded by 4 times our separate free mechanism in the proportional complement setting. Okay? So that proves our theorem. This is just a recap of what we said. So now the grand bundle was the same. We bounded the fully boosted separate revenue by 4 times the separate free, and that gives the 12 max of these two. And I just very quickly want to say that we can extend this for the hypergraphs. So this is like taking the maximum over iWork and Word and Google Drive. And what we get is a minimum of D and K. In this case, I did not say what D and K are. Okay, so what D is, again, is the maximum degree, and K is the size of the largest hyperedge. And the way that we do this is that to get a K, we take each item free independently with probability 1 minus 1/2K. And to get the D, we take each source of a hyperedge, so it's like a bunch of items directed into one item, and we take that hyperedge to be free with probability 1/2D, and if an item never winds up being free, then it winds up being priced. And so these are our modifications to the mechanism. To get these factors, we take whichever one gets the minimum, and that's our approximation. That's all. Thank you.
Questions? I'm not sure I fully understood the model, but do you have substitutes, strict substitutes in this model?
We have maximum over hypergraph, so that's the only type of substitute we have. Yeah. But all of the etas are positive. Yeah. Yeah, Matt.
Do you know if these bounds are tight or asymptotically tight?
No, we have a lower bound that matches our analysis, but that's it for the K. Yeah. Yes.
Do you know if it's simpler for the case of symmetric boosting?
What do you mean?
So the edges are not directed.
Oh, that's a good question. I don't know, but I'm not sure it would change that much. I'm not sure it would change that much, but I don't actually know. Yeah.
Thank you so much.